Hi again. This is a short presentation on thin film interference. It covers chapter 24 in your book, or part of chapter 24. And it's a really fascinating phenomenon that we see with light. So let's go. So here are two examples of thin film interference. The one in the upper left here shows a television set, kind of like the one I buy because I'm cheap, that has a lot of glare on it from the outside, so I can't watch Netflix during the day. But this one here has a thin coating on it, and so it stops the glare from coming in to the TV, so you can actually watch TV. And this guy over here, I'll put a little smiley face, is a soap bubble. And you can see, we often see rainbows on oil slicks and soap bubbles that we blow in the air. And so why do we call this interference? Well, we're going to learn that. Some of the light rays that are coming off the surface of this bubble are interfering constructively and destructively with other light rays that are coming through the soap bubble. And we're going to look at how that works. And if you want some animations of cool soap bubbles, I left this URL up here in this presentation, or just Google cool interference patterns. So just as a review, waves that occur in the same space can add to form a new wave. And if they add completely, so if the waves are almost in phase, we call that constructive interference. And it's when the peaks and the valleys or the crests and troughs are perfectly lined up, or mostly perfectly lined up, as you can see in this picture. Now this will happen if the waves are perfectly lined up or if they're shifted by a complete wavelength. So if I took the blue one and shifted the blue one from here to here, for example, it would still line up perfectly with the red wave and we would still get constructive interference. With destructive interference, the two waves are not lined up perfectly, but they're shifted by half a wavelength if we're dealing with the distance axis, or you could say by 180 degrees, any way you like to think about that. So we're going to talk about the blue wave being half a wavelength, or 3/2 of a wavelength, or 5/2 of a wavelength shifted from the red wavelength. And when they add together, or when they meet in space, you won't see anything or hear anything. If that was a sound wave, they would cancel out. Sidebar, this is how noise canceling headphones work. They create a wave that they mix with the sound coming into the headphones, and they create kind of an inverse wave, or a wave shifted by half a wavelength, and they add it together and it cancels out that ambient noise. But we're going to look at how that works with light. So just in summary, if the waves are one wavelength apart or a multiple of a wavelength, we will get constructive interference. And if they're half a wave out of phase, or a multiple of half a wave, we will get destructive interference. So how does this work with light? Well, let's talk about how can light be shifted by a wavelength or half a wavelength. Imagine we have one beam of light here, beam 1. And sometime over here, beam 1 was split. So beam 1 kind of comes down this way, and it gets split and goes along path 2. So the path length for beam 2 is longer than beam 1, and they meet up kind of over here. Now, the extra length that it's going to make this little triangle from here to here, this extra path length, the difference between this triangle and this straight line here, I know I'm making a mess. If that difference is equal to a wavelength, or is a multiple of a wavelength, we will get constructive interference for these two waves, as shown in this formula here. However, if that difference in path length, so again, this path length and this V, if the difference between those is half of a wavelength or a multiple of half a wavelength, then when those two waves meet together, we will get bupkis, bagel, not on Nix, whatever you see, a flat line. And we can kind of see a formula down here. It looks like a funky formula, 2m minus 1. You can imagine if m was 0, this thing would collapse to lambda over 2. If m was 1, we'd get 3 lambda over 2. And if m was 2, we get 5 lambda over 2. So any multiple of half of a wavelength. And that's what's happening in thin film interference. Most of the colors are canceling out or not creating constructive interference when the light passes through and reflects off of a film. But one wavelength in particular is bouncing and creating its specific constructive interference because the geometry of the film is perfect. And we're going to look at that now. Just as another sidebar, because we like to do sidebars, it doesn't always work with really long, in fact, this doesn't work with really thick films or with all kinds of light. The light needs to be coherent. That means all of the light that's coming in and bouncing around needs to be in phase. And in phase means what we would consider, what we would draw on a physics board, one continuous waveform like you see on the bottom. When we create light over long distances, maybe it's from an incandescent bulb, or if it's bouncing around somewhere, that light is not a smooth waveform, and you get different jumps, and you don't get this nice ability to add and subtract waves that we would with coherent light or with very, very thin films. So it doesn't work all the time. It doesn't work this thin film problem. Why is it a thin film? If it gets really thick, the light becomes incoherent and doesn't add the way we just described in the previous slides. Okay, so here we go. We can look at this this film here, and you can see lots of different colors. Why would there be different colors? Well, a soap bubble or an oil film has many different thicknesses, and you also look at it at different angles, but those thicknesses are defining different path differences or path lengths for the two different beams of light to meet up. So what different beams of light are we talking about? We kind of look up here on the left, we have a beam of light that's reflecting off the surface here, off the top surface, and then another beam of light, which is from the refracted ray that's then bouncing back and then refracting back into the air. And I know this is a very chunky diagram, but I'm still learning how to do this. But these are the two light rays that we're talking about. If they meet up and add together, like they might over here for this orange, then you're going to see the orange light and you're not going to see any of the other colors. And we're going to look at how the geometry works momentarily. But these are the two beams of light that we're talking about up here. And this is the extra path length that we're talking about here, this little V from the refracted light reflecting off the bottom of the film. So this is a nicer version of the same picture. Here we have our incident light right here, and it is reflecting off here. It's also refracting into the bubble, reflecting off the bottom of the bubble or the film of oil, and then back into the air. And these two beams are what we care about when we're analyzing this problem. This beam here and this beam here. And you can see it happens many, many, many times, but for analysis sake, we're just going to look at these two. The rays reflected off the lower surface of the bubble, so this bubble or film, this lower surface, these rays have traveled a longer distance than the rays reflected off the upper surface. If the optical paths differ by a multiple of a wavelength, then we get constructive interference. And if they differ by half of a wavelength, then they're going to cancel out. And so maybe you're thinking, oh, now I kind of understand this because different colors of light, red, orange, yellow, green, etc., have different wavelengths. So this thickness that we're looking at has to be related to the wavelength in order to create constructive or destructive interference for a specific color. Okay, we need to step back just a minute because this is a weird phenomenon that we're going to accept as fact and say, okay, whatever, physics says it's so. We're not going to push it too much. But if I have a surface where, let's say this is air, n is 1, and this is anything else, n is greater than 1. So the top surface is n is bigger than the bottom surface is n. That's very important. This ray coming in, this number 1 ray, when it reflects here, it is already shifted by half a wavelength. There are reasons behind that. We won't go into that now. But when this n1, the top n, is bigger than the bottom n, the reflected ray is shifted by 180 degrees or by half a wavelength. Basically, if you picture a wave coming in here, coming up, down, and we're at the bottom of the wave here, then when it bounces off, it's all of a sudden at the top of the wave. So we get a flip of the wave when it goes from the incident to the reflected ray. That doesn't happen if the top n is greater than the bottom n, but in this case it does. Maybe make a note of that or come back to this slide, or just say, wow, that's weird, but I need to use it. Solve a problem. Okay, so let's take this little diagram of the whole ball of wax. So we have this incident ray coming in here, and when it reflects, it's shifted by half a wavelength. So we are already out of phase by half a wave here. So we want to compare that wave with, let's say, this one here. So this extra distance from here to here. This is an extra path distance, right? That the top ray number 1 did not use. So we go the refracted and reflected off the bottom surface, whatever this distance is our path difference. We are going to assume that this little v is actually twice the thickness of the film. We can see that it's not. We can do some Pythagorean theorem and look at the refraction angles. But for simplicity's sake, we're going to assume that we're talking about a perpendicular distance. And this v is only here for diagram's sake. So the extra path distance that this light ray travels is twice the thickness of the film. It doesn't look that way. We're gonna love this. All right, so we're just gonna assume it's true, use this for diagram's sake, and see how we solve the problems. All right, so if this extra path difference is equal to half of a wave, if this thickness 2t is equal to half a wave, then when this light comes out here out of 2, it will be in phase with this because this one has already been shifted by half a wave. So this one's shifted by half a wave. If this extra distance is half a wave, then these guys are going to line up beautifully, and we're going to get constructive interference for that cone. If this path length here is equal to 1 wave, a full wavelength, then when 2 comes out the top here, when it pops out here, it's going to be half a wave shifted from this, and it will be destructive interference. And so we've got 2 formulas down here. This is my formula for constructive interference. M, again, is an integer from 0 to 1 to 2. So it can be half a wavelength, 3/2 of a wavelength, etc. And for destructive, the formula is down here, where we want to have 1 wavelength difference in path length. Where did the N come in? Great question from the back of the room. Didn't know you guys were paying attention. Why is the N in here? Well, the wavelength in the medium, lambda sub n, so the wavelength in here is less than the wavelength up here. Because remember, the speed of light is slower in the medium than it is up top. And it's slower because of the index of refraction, and the formula pops out here. You're going to see this in an example coming up. But the lambda that we're talking about in this equation here, right, is really lambda over n. So that's why this n pops up on the other side of the equation. Confused yet? All right, pause, take a break, run around the house, and come back. So this is a nice picture of of what I just talked about. And again, n is greater than 1 here, so we're going to get that half shift at 2. This is how anti-reflective coatings work, like I showed on the TV, or sometimes we see them on optical equipment to get that glare off of a lens or a mirror or something like that. Probably not on a mirror. That was just me blathering for a minute. But what we want to do is we want to cancel out as many wavelengths as we can. And you can imagine, as another sidebar, if T is really, really thin, we're going to be able to get a lot more waves canceled out because we're going to get half a wavelength shifted from the reflection. And then if this path length is really tiny, for the most part, these two are going to be 180. These two are going to be 180 degrees out of phase. So I'm just going through a couple more clarification text bullet points. If we have a really, really thin film, as I just said, then pretty much all the wavelengths are going to be canceled out and the film appears black. So we're basically wiping out all of that incident light. And that's what you're going to see on the surface of your anti-glare television sets. That again, Mr. Fissler was too cheap to buy. This is just another little picture that I saw on the internet, which I thought was pretty cool. But what I liked is that the blue light is going to be the one adding where it's thicker, and the violet light is going to be the one that's adding where it's thinner. This one went through a longer path length, and so the longer path length, the longer wavelengths are going to be additive, and blue has a longer wavelength than violet or magenta, or whatever you want to call it. Just don't call it indigo, remember. All right, so let's see how a problem works. So if you've ever seen a camera lens, sometimes you look at it and you see a color, like a greenish yellow color maybe, or whatever color might be reflected. You don't see the whole sunlight reflected off of it. So in this case, it appears greenish yellow, which has a wavelength of 570 nanometers. And I want to know what's the thickness of coating, and the coating thickness has an N of 1.25. That can be used on glass to produce this effect. So we have air, then the coating, then the glass. And so the light is reflecting off the surface of the coating, refracting through the coating, bouncing off of the glass back to the air. Just like this. Now take a look down here. This is a little different than what we talked about before. Here we've got N as 1. Here we've got N as 1.25, and here we've got N as 1.52. So the N is getting bigger from here to here, and it's getting bigger from here to here. So at this reflective line here, we're going to get that 180 degree shift, or the lambda over 2 shift here. But down here, we're also going to get the lambda over 2 shift, because this n is smaller than this n. So there isn't any magic bullet to solving these problems. You just got to understand how things are working. So for this problem, we have this situation. We have again, the light coming in, bouncing off and shifting by lambda over 2, coming through the coating and bouncing off, and we have another shift here of lambda over 2 because this n of 1.25 is bigger than this, smaller than this n of 1.52. So this path difference from here to here has to be equal to 1 wavelength of light, because we want these two guys to be exactly in phase. And that's equaling 1 wavelength because we had a flip here and we had a flip here. If we didn't have a flip at the bottom, it would be lambda over 2. But for this case, 2 times the thickness is equal to 1 wavelength. Now, which wavelength are we talking about? We know in air, the wavelength was 570. But in the medium here, the wavelength is 570 divided by n, divided by 1.25. So we need to divide this wavelength, the 570, by 1.25. So we get twice the thickness is 570 nanometers divided by 1.25, and you get the thickness of 228 nanometers. Again, somebody in the back, check it on your calculator. I am old and I can't see anymore, and maybe that's not the right answer, but I'm pretty sure it's the right answer. As a sidebar, for destructive interference, twice the thickness would equal half a wave in this example. So the thickness would be lambda over 4. But remember, lambda is lambda over n, so we get in a formula looks like lambda over 4n. All right, that's a quick example. Read the chapter in the book. I believe it's chapter 24. There are some nice pages on this. There are sample problems in the back, or problems I asked you to do. The solutions to this problem will be posted on Canvas very shortly. And please email me with any questions. So I wish you all a wonderful day, and I wish you peace, love, and Purell. And please keep in touch, and hopefully we'll be on Google, I forget what it's called, Google Meetup soon. Thanks.